Hello, today we're looking at topic 3.13, trigonometry and polar coordinates. So this is our first lesson in polars. And up until this point, the only system you learned to be able to graph in was the rectangular coordinate system. You started learning how to do that a long time ago. And in this system, it uses an x-axis and a y-axis, and all the points are described with the ordered pair x, y. So this rectangular coordinate system, also known as the Cartesian coordinate system, think about it as being very similar to a road grid. In other words, if you're driving somewhere on a road, we have to go over and then up to a definite point based on the roads that we have to get there. In other words, we can't just drive through someone's yard or something like that. We've got to stick to the roads. And most of those are laid out in a grid in different towns. So that's that Cartesian system. But what we're going to learn today is an alternate way to describe points in space, and this is called the polar coordinate system. With polar coordinate systems, we don't use an x or a y value to graph a point. In the polar coordinate system, this is much more like flying in a plane. Think about that. I know where the airport is. The plane takes off at a certain angle or degree or measure, and it flies to the point. And we can go pretty much anywhere as long as there's an airport there for us to land in. So to define a point in this system, we only need the angle, and then that's the angle of a point that's going to be in standard position, which we know means starting at the positive x-axis and rotating counterclockwise. And then we need to know the distance of the point from the origin. And it says signed right there because we can reverse direction with a negative sign, and we'll talk more about that in a minute. So it's not that the radius itself is negative, it's that we have a radius and then we can apply a direction down that radius. So in other words, we simply rotate until we're facing the point, and then we draw a line directly to that point from the origin. And so that's kind of a little different than what we've been doing because we don't have to have any set x and y to get us there. Polar coordinate systems can be really useful, especially when you're working with circles and trig functions, conic sections, things like that, where we have not just our traditional XY direction or position to get there. So we're going to start first by looking at what polar coordinates are, and that's a big part of what today's lesson is. And so we have our polar coordinates, and the polar coordinate is this point here, A, on your graph, and notice it says r theta. So in polar coordinates, we're defined by that radius with direction and theta, which is an angle. Now keep in mind, r does represent a radius. So when we talk about the radius itself, we're talking about the absolute value of r. But we can use direction, so we could make that negative, not that it's a negative radius, but that we're going to apply the radius in the negative direction. And so when we put that theta, we represent the measure of the angle in standard position. And then that means in standard position, that terminal ray is what we're looking at. And that's going to include that coordinate point that we're talking about. So we still have our standard position going on here. So one of the really cool things about using polar coordinates is the same point can be represented in a whole lot of different ways, especially since technically a circle goes on forever. So we could keep naming and renaming points in different ways based on what we were doing, how many times around the circle that we're going to go. Okay, so we're going to start by practicing just doing this label. Now, one thing that's different in the Cartesian system and the polar system, in the Cartesian system, we do the horizontal distance or the x first and then the vertical distance. In polars, we actually graph the angle first and then the distance. So notice the angle is the second piece of the coordinate. So we're actually starting back here with the angle and then applying the distance of the R to begin with. All right, so we have this grid. Notice it's a circular. And as you can see, these rings around here, those represent distance. In our particular grid right here, 3 rings represents one number, and then 3 more rings gets us to 2, and then 3 more rings gets us to 3. Also notice that in this axis, this right here is not one of your 3 angles that we've been looking at. This is pi over 6, pi over 4, pi over 3. So we do have these distances here. So basically, it's about, different increments, but we can still use what we know about these points, pi over 2's, pi, 3 pi over 2's, to help us figure that out. Okay, so on this same axis, we are going to plot 4 different points, okay? So remember that the first thing we do is start with the angle. So my angle is pi over 3, and this axis right here in polar system is called the polar axis. That's the positive x-axis in the rectangular system. And notice that you have a center on this graph. In the Cartesian system, that's your origin. In the polar system, that's the pole. So sometimes those words will get interchanged. Sometimes we'll be in the polar system and people will say at the origin, and then sometimes they'll say at the pole. So just being familiar with that term. Okay, so let's plot A. So we're going to start at pi over 3, which is right here. And then along this line from the origin, I'm going to plot out to the 2. And remember, 3 rings makes 1. 3 more rings makes 2. And so once I get here, I have this point, which is A. Okay, that's kind of cool, yeah? All right, so let's look at B. So B, I'm going to be at 3 pi over 2. So starting at the pole axis and going around here to 3 pi over 2. So we're down here. And then we're going to go 1 count or 1 numbered count from the pole or the origin. So from here, and remember this is the 1 ring right here. And so then I go down here and I put that dot on that 3 pi over 2 angle, and that is my B. All right, so let's look at C. So C, I need to know where 4 pi over 3 is, and 4 pi over 3 is going to be the other side of my angle down here, right? So if this is pi over 3 on this side, if I continue down here into this quadrant, that's where my 4 pi over 3 is. So we can kind of use those angles to measure, because we know that we can count around, and 4 pi over 3 is in the 3rd quadrant. And then from the pole, then down that line, I'm going to go 3, which puts this point all the way out here, and that's point C. Make it dark enough so you can see it. Yeah? All right, so the last one, negative pi over 6, that means from the pole axis in the negative direction would be negative pi over 6. Don't forget that extra marker here. So we're going to be here at pi over 6, negative. And then from the origin, from the center, from the pole on this line, we're going to go out to the 2 marker, which is out here. And that's going to be D. Now, sometimes you may be counting every ring as a 1, 2, or 3. It just kind of depends, just like you have scales on X and Y axis. On that radius, it can have a scale too. So we always want to pay attention to markers that tell us how far out is our first one. So this is 1, this is 2, this is 3. Okay, so not too bad, I hope. So let's move on to example 2. In example 2, we have these 4 points. We're going to plot them. Notice on point D, that's a -2. Does that mean the radius is negative? No, it does not. It means the radius is 2, but in the negative direction. And so we'll talk more about that when we get to plotting D. So let's just start here and plot the first one. So pi over 4 is right here. And I want to come out a distance of 2 down that graph, and my 2 at pi over 4 puts me right here, and that's A. Okay, so now let's look at B. So B is -7 pi over 4. So I'm starting at the pole axis, and I'm going around here, and this angle right here, yes, it's pi over 4, but it's also -7 pi over 4. And on the -7 pi over 4, we're going to go out 2 places down that ray. And so that puts me at the same place right here, which happens to be same point. But now we've labeled it B because that had different coordinates that let us land in the exact same place. All right, so now let's go to point C. So 9 pi over 4. So 9 pi over 4 means we're going all the way around. And so that would be 8 pi over 4 plus 1 more pi over 4 puts us once again up here at 9 pi over 4. And then from 9 pi over 4, we're going to go down that ray too. And so now we have point C at the exact same place. So finally, let's do the last one, which is going to be D. So where is 5 pi over 4? So if this is pi over 4, then this is going to travel down here into this quadrant because I know 5 pi over 4 is in the third quadrant. But look what happens. It's not just going 2 down that ray toward 5 pi over 4. It's reversing the direction of 2. So 2 units, but in the reverse direction. So remember how we connected these lines right here? That means from the pole down the pi over 4, I'm going to go 2. And that's going to make my D at exactly the same place. So all of these points are at the same location. Okay, so 4 representations, all of them happen to be at the same location. So example 2 illustrates how a single point in a polar coordinate system can be expressed in many different ways. In fact, there are infinitely many ways that you could express any given point on the coordinate plane. So that's very different from the rectangular system. In the rectangular system, a point is a point. Here we can use different ways to represent the points to be able to look at those multiple representations. All right, so let's look at the next one. So in example 3, we're going to plot the point with this polar coordinate right here on the grid above, and then we're going to write that polar coordinate in at least 2 different ways. And we're actually going to do 3 different ways just so you can see all the possibilities. And to do this, we're basically going to use what we know about coterminal angles. We're going to use what we know about rotating in the positive and the negative direction to get our angles. And then we're going to use what we just learned about reversing direction and using the same direction to plot the points. Okay, so the first one that we have is 3, 5 pi over 6, and that was the original point. Okay, so that's just this point on the graph that we're going to graph by doing 5 pi over 6, which is going to be in the second quadrant right here. And the distance is 3. So this is 5 pi over 6. And from the pole out, because remember, every 3 lines makes a count, so that puts it at 3. So that's the original point. All right. So that meant we started from the pole axis. We opened counterclockwise in the positive direction to 5 pi over 6. So the first part that we're going to do then is what happens if we rotate in the negative direction. So if we go from here to this same angle right here, we know in the negative direction it's negative 7 pi over 6. So my next coordinate that I'm going to have is going to have an angle of negative 7 pi over 6. Now, if this is at negative 7 pi over 6, to get that dot in the same spot, then I go from my pole or my origin down the line 3 times. Okay, so what I did was I used the negative angle and the same radius. And I am just writing this out because these are your notes. So I want you to be able to see what we're doing here. So I started at the pole, positive direction, counted out 3. That's the original. Went in the negative direction to the same angle, counted out 3. And so now I have 2 points at this same location. Okay, so now remember that the angle that we have been graphing on is this right here, down to the pole. So what we're going to do now is we're going to keep going down that line in the quadrant 4. Oops. Okay, so we're going down to there. So sorry, I got my little mix up right there. And then what would that angle be if I'm going from the pole all the way around in the positive direction? That angle is 11 pi over 6. Okay, are you with me? So this is 11 pi over 6. But if I plot positive 3, then that means 3 down toward 11 pi over 6. And that's going to put my point down here, not up here where I want it to be. So I'm going to use this angle of 11 pi over 6, but I'm going to reverse the direction that I plot my radius, and I'm going to go backwards up to this point. So that means I need to make that negative 3. So what does that mean in terms of what you did? Basically, we are looking at getting the angle at 11 pi over 6, and so I went in the positive direction, and then I reversed the radius. So same radius here was 3, but the reversed radius here would be negative 3. Okay, so positive angle from the pole to get the other half of this line down here. And then I reverse the direction of the radius so I could plot my point back that way. All right, so I'm hoping that maybe you can see where the next one might be. So if we went here and went around in the positive direction, then what else could we do? Hopefully you can see we can go in the negative direction. So I could do negative 11 pi over 6. So from the pole down here, now think about that radius. Do I want a positive radius so that it will graph and be down here? Or do I want to reverse the radius direction and plot it up here? And hopefully you can see that we want to reverse that. So that's also going to be negative 3, which means in this case, we use the negative angle and then we reversed the radius. So that would also be negative 3. So you can see that you do have to be careful. Make sure you get the right direction of your angle there in your plotting your points, because it's really easy to go, oh, I'm going to go to 5 pi over 6 and then reverse the direction, or say, I'm going to go down here to negative pi over 6, but I'm going to keep the 3 and forget to reverse it and shift it back up here. Because remember, this is what we're trying to find, is points that represent that location. Okay, so now let's talk about how do we connect rectangular and polar coordinate systems. So if you look at what we have been doing, when we graph something in the rectangular system, we would go horizontally, which is our x distance, and vertically up to be our y. So we have x distance, we have y distance, and that gives us that coordinate point. So we have x, we have y. So our point there would be x comma y. All right, so in the polar system, we have an angle that gets graphed from here to here, and then a distance down that angle that is radius. So the point in the polar system is our theta. The point in the rectangular system is x, y, and they can be connected when we kind of put these together. So imagine that we have our x and our y distance that gets us to A, or we have a distance from the pole that's an angle, that we're talking about the angle from here to here, that gives you that A. So that's how they're connected together, is we can look at that horizontal and vertical distance, we can look at what we know about the angles. So the image on the far right, that's this box right here, allows us to connect between X and Y and the polar. And we can use this to quickly find relationships that allow us to convert between polar coordinates and rectangular coordinates. And so that's what we're going to kind of focus on first. We're going to convert from polar to rectangular coordinates. In order to do this, when we are doing these conversions, we are going to go and use what we know about cosine and sine. So we know that cosine theta is x over r, and then we know sine theta is y over r. So we learned those a long time ago. So if I want to get r from not being in the bottom of my fraction and I want to know what x equals, I multiply both sides by r, and that gives me x equals r cosine theta. And then if I do the same thing with my sine values, multiply both sides by r, then I can rewrite that as y equals r sine theta. And so these are the conversion pieces that we're going to use when we start with a polar coordinate and we want to end with a rectangular. So basically the tip for this is whenever you're converting coordinates from one system to another, I would always recommend doing a really quick sketch of the point first, and then that allows us to check our answers and make sure that they make sense. So we have some number sense since we don't know a lot about the system at this point. Okay, so we're going to start here with 2 comma pi. So if I plot that, remember I plot the angle first, which is over here at pi, and then I'm going to go down 1, 2, and plot my point. So that's the graph. Okay, so in order to do the mathematical conversion, then I'm going to say x equals, and what's my radius? 2 cosine of pi. So we should know cosine of pi from our unit circle, so that's going to be 2, and the cosine of pi is -1, so then x is going to equal -2, which makes sense when we look at our picture. The x value would be -2. All right, so then to do our y, then we're going to do y equals, and the radius is again 2, but this time it's sine pi. And so then I'm going to have 2 times, and what is the sine of pi? It's 0. So I'm going to have y equals 0. So what I just found is the coordinate point in rectangular system, which is just -2, 0. So look at this point. What was the coordinate in the rectangular system here? We go over -2 and stay put for 0. Or in the polar system, I'm starting at the pole axis, graphing around to pi, and then down that ray, 2 points. So if you're on an axis, then sometimes you can reason through these by just knowing all of the stuff we've been learning so far in our class this year. All right, so first off, let's plot B. So B is going to be at 5 pi over 3, and 5 pi over 3 is going to be in which quadrant? So we're going to be down here, and then 4 down, so 1, 2, 3, 4. So that's where this point is. So that's this coordinate point. All right, so let's use our conversion fact. So we're going to say x equals, the radius is 4, and then I'm going to have cosine of 5 pi over 3. And so according to our unit circle, cosine of 5 pi over 3 is 1/2. So x is going to equal half of 4, which is 2. And then we're going to do that for the y's. So y equals 4 sine of 5 pi over 3. And so y equals 4 times, and sine of 5 pi over 3 is -√3 over 2. So then when we simplify for our y, 2 is going to go into 4 2 times. 2 times -√3 is -2√3. So then we have our coordinate point that we just found. that is 2 comma negative 2 root 3. Well, does that make sense? What is root 3? Root 3 is a little bit bigger than 1.5. So if I'm multiplying 1.5 by 2, that's roughly about 3.46. So let's see, negative 2 root 3 is approximately 3.46. Okay, so does that make sense? Look at where this point is. It's positive direction 2. That makes sense. Going down to the negative 2 root 3, which is at, maybe negative 3.4546, something like that. And so, yeah, this point does make sense with this coordinate. All right, so let's look at numbers or letter C. So we're going to graph this first. So when we graph, we're going to need to find out where 7 pi over 6 is. So where would we find 7 pi over 6? We would find it down here, 7 pi over 6. But notice the 3 says we're going to reverse direction. So that means I'm looking at this side of my graph, and I'm going back 1, 2, let's see, 1, 2, 3, and the point is going to be plotted there. So 7 pi over 6, but reverse the direction from the pole, 3 units. So it's going to be graphed somewhere up there. All right, so then if we do our conversion, then we're going to have x equals the radius in reverse direction is negative 3 cosine 7 pi over 6. So we know negative 3 times and cosine of 7 pi over 6 is negative root 3 over 2. And so x is going to equal negative 3 root 3 over 2. All right, so then we're going to do the sign. So we would say y equals negative 3 sine of 7 pi over 6. And so that's going to leave me with negative 3 times, and the sine of 7 pi over 6 is negative 1/2. So the y here is negative times a negative, or a positive 3/2. So we're saying that the coordinate point then would be 3 root 3 over 2 comma 3/2. So we know that the y is about 1.5, so that makes sense. Root 3 is about 1.73, so 3 of those would be about 5.19 or 5.2, and then half of that would be roughly 2.59. So about 2.59 up that would be approximately a good calculation. So what I did is thinking through this in my head. I said root 3 is about 1.732. And then I said 3 of root 3s. So that got me about 3 times. So I was like, well, that's about 5.19 or 196. And then I said, okay, so now I'm going to divide by 2, cut it in half, and that's approximately 2.59. And the reason I'm doing this is not that I expect you to necessarily do all the computations, but I want you to have some way to reason through and make sure, does this make sense the way I'm doing this? Does this answer make sense? Does 1.5 make sense to where I would have plotted that point to begin with? Okay, so we went from polar to rectangle. So now we're going to go from rectangle to polar. Okay, so let's look through our information about converting from rectangular to polar. So the rectangular point we got by plotting x and then y, and now we want to change that and be able to plot the angle and then the distance up the angle. So in order to do this, the things that we use to convert with is to get the radius, we're going to use Pythagorean theorem. And then to get the angle, we're going to use the tangent of theta is y over x, and that's going to help us find the angle. So Pythagorean gets us the distance down the ray, and tangent gets us the actual angle itself. And just like before, the tip here, whenever you're converting back and forth, it's always a good idea to sketch the point first and see that your answer matches it and makes sense. So that's what we're going to do, just like we did on the last one. So the first thing I'm going to come down here and do is graph this point. And this point graphs at -2, +2. So I'm right here at -2, +2. So there's my point. And so as I go through this, I want to keep in mind this is my X and this is my Y, and that's what my point looks like. Okay, so to do the first part, to find the radius in polar coordinate point form, I'm going to use Pythagorean theorem. So I'm going to say -2 squared plus 2 squared equals r squared. And so I get 2 squared is 4 plus 4 gives me r squared. So I now know r squared equals 4 plus 4 or 8. All right, so now how do I get r? R is going to be, and remember we're talking about distance, so that's going to be √8. Oftentimes you're going to need to break that down because, as I said before, this is heavily going to be multiple choice questions, and I would venture to say there's probably not going to be a √8 there. So if we were to break that down, then the 4 times 2 is 8, so that could be 2 root. So I can take 4 and take the square root of 4, which is 2, and then I'm left with 2 underneath. So in other words, that would be 2 times 2, which is 4 times the radical 2. All right, so just making sure you understand that could be another way to write that. Okay, I'm not necessarily all the way through, need to do that every time. But especially multiple choice, you need to be sure that if you're using this as your answer and you don't see that as an answer choice, that you know how to rewrite that radical to get you here. So, because that's probably going to be a choice. All right, so now that we have found our radius, then we're going to use tangent. So we're going to say tangent of theta equals, and then we're going to do y over x. So that's going to be 2 over -2. So tan of theta equals -1. And what angle in this quadrant, quadrant 2, has a tangent value of -1 when theta equals 3 pi over 4? So then this rectangular coordinate is going to be a polar coordinate that looks like square root of 8, comma, 3 pi over 4. And did I get all of the characteristics? Is the second piece in my coordinate an angle? Is the first piece a distance? And so these are the two ways and two things that we use to convert from rectangular to polar. So always pay attention, where are you starting and where are you ending, so that you know if you're going to be doing x equals r cosine theta, y equals r sine theta, or are you going to be using Pythagorean theorem and tangent? Okay, so let's look at the next one. So we're going to graph that first. So when we graph this one, then we're going 1 in the positive direction and then down in the negative direction. So I'm going to down here. So that's going to be between 1 and 2, and then this is going to be down 1. Okay, so um, when we're plotting this point, hold that thought for just a second. I just saw a mistake. Oh, phew, I didn't make a mistake. I was thinking back to a minute ago when we were going in the other direction. All right, so sorry about that, folks. So this is between 1 and 2, and then it goes down to -3. So we're talking about something that's in the fourth quadrant. So we're going to use our conversion facts. So we're going to say 1 squared plus -√3 squared equals r squared. So 1 squared is 1 plus, and this negative times a negative is a positive. Square root of 3 times square root of 3 is square root of 9, which is 3. And that's what r squared is going to equal. So 3 plus 1 is 4. So r, the absolute value of r, is going to be 2. Okay, so now we know the distance down the angles, so now we just need to find the angle. So to find the angle, remember we're going to do tangent of theta, and we say theta because we don't know what the angle is. You could say x if you want to say tan x, that's okay. And then we do, I don't usually, because when we're going back and forth, we're talking about X and Y anyway when we're plotting points. So I typically use theta as my angle. And so then to use theta, I'm going to do the Y value, which is negative root 3 over the X value, which is 1. So tan of theta equals negative root 3. And what has a tangent value of negative 3 in quadrant 4? What angle? That angle is going to be 2 pi over 3. Okay, so let me finish my thought here. I started with finding that the one of the angles that has negative root 3 would be 2 pi over 3, but I never finished my thought and actually looked at what would be the second angle that could have that same value, which would be 5 pi over 3. So if I look at 2 pi over 3, that's in quadrant 2, and then 5 pi over 3 would be in quadrant 4. So of these two angles, which one is going to give me an angle that's going to be down here where that original plot was that I plotted? All right, so I'm going to have a radius of 2, but I'm not going to use the 2 pi over 3. I'm going to use the 5 pi over 3 to make sure that we're talking about this point that we plotted. So does that make sense? Yep, that's about 5 pi over 3. And then I'm going to go out 2 rungs down. All right, so let's look at the next one and start out once again by plotting the point. So we're going to be up here, and it's going to be 0, negative 5, right here at negative 5. Okay, so once we have that, then we use the Pythagorean theorem to find the distance down the ray from the pole or the origin, and then we use tangent to find the angle. Okay, so I'm going to have 0 squared plus negative 5 squared equals r squared. So I get 0 squared, which is 0, negative 5 squared, which is 25. So 0 plus 25. I'll go ahead and write it out just so you keep track of everything. So now I need to know r squared equals 25. R, or the absolute value of r, is going to be 5. And that, because we're going to be down here. And then we're going to use our tangent to find our angle. So tan of theta is going to be, and then we use the y, which is, so this is tangent, which is sine over cosine. So we have a problem here, right? We can't divide by 0. So this conversion fact isn't going to be very helpful for me right now, but all of my prior knowledge in trig certainly will, because what is the angle that goes from here around to this point? 3 pi over 2. So we could say that we have a converted point here then of 5, which is the distance, and then we're going to do 3 pi over 2. So does that make sense? Well, if this is 3 pi over 2 and I want to go down toward 3 pi over 2, then I have to be going in this negative direction, a distance of 5. So remember, if this is the angle and we're plotting on the angle toward it, then that's going to be positive. If we were needing to reverse it and get a point up here, then this would be negative 5. So you kind of have to think about the placement of the point, which is why I really prefer if you start by graphing those points so you have that visual to fall back on. So does everybody understand that we went from here around here to get the angle 3 pi over 2? And because I needed to graph down to that 3 pi over 2, I want to graph toward 3 pi over 2, or 5 units down, which would put it at negative 5. All right, so the last thing we're going to talk about is complex numbers. So imaginary numbers didn't go away. Previously, we have written complex numbers using complex form, which is a plus bi, where a and b are constants. So a and b are constants. A complex number can be understood as a point in the complex plane that can be determined by its corresponding rectangular or polar coordinate. So a complex plane, so it can be determined by either corresponding rectangular or polar coordinates. In other words, I can take an imaginary number and I can define it in a rectangular system like we did earlier in the year and like you learned in Algebra 2, or we can take this same point and define it in the polar coordinate system. All right, so complex numbers are a little different in that regard. So when a complex number has a rectangular coordinate AB, then it can be expressed as A plus BI. The complex number 3 plus 2i can be represented as the point 3, 2. So it's a connection there in the rectangular coordinate system. Will they always be nice and pretty? No. So it's important that you know how. Earlier in these notes, we reviewed the fact that we can use y equals r cosine theta and y equals r sine theta to convert points. And using these identities, we can also express complex numbers in polar system. So that's what we're going to do. So when a complex number has a polar coordinate, it can be expressed as r cosine theta plus I r sine theta. So here's my x, here's my y, don't forget the I. Okay? So as we look at this point 3.2 up here on our graph, we can write that as the complex number 3 plus 2i, and then we could also convert here. Okay? So example 6, a complex number represented by a point in the complex plane. The complex number has a rectangular coordinate of -2, 2. What is one way to express the complex number using the polar coordinate r theta? All right, so how we're going to work on this one is we are going to use those conversion facts, x equals r cosine theta and y equals r sine theta. And then we should be able to get to our rectangular coordinate. Okay, so here's what we have. We have 2 and -2. So I'm going to plot that just like we've done all of the other things that we've done. And so we're going to go -2, -2. So we have this point down here at -2, -2. All right, and so then we're going to be looking at what angle goes through that point and has that distance, and that's how we're going to connect that to the polar stuff. All right, so on example 6 then, if I want to know the radius of my circle, then I'm going to do -2 squared plus -2 squared equals r squared. So -2 squared is 4 and 4, so we have 8 equals r squared. And so r is going to equal square root of 8, or r can equal, break it apart, perfect square 4 times 2. So I get 2 root 2 as the approximation. Okay, then we're going to look at the tangent. So tangent of theta is going to equal, and then I have my y over my x. So tan of theta equals -1. And so what angle has a tangent value of -1? Well, first off, before you find that, that should be -2. So it's -2 and a -2. So we're not looking for when tangent is -1. We're looking for when tangent is +1. Sorry about that. I seem to be making some silly mistakes here at the end. We're almost finished, so we'll get through it. All right. So now I have tangent of 1. And so I know that that can happen at quadrant 1. So think about it this way. So we have it up here and we have it down here. So it can be pi over 4 or 5 pi over 4. Okay. So of those two, then, which would I find in the third quadrant? I would find 5 pi over 4. So now I know that angle and I know the distance down the angle. So I'm going to come up here and put it in my complex form, which is right here. Okay. So then I'm going to have square root of 8 cosine 5 pi over 4 plus, and then I'm going to have my I, and then I'm going to have square root of 8 because that's my radius, sine 5 pi over 4. And that is my complex form. Okay, so if I wanted to prove that this was in fact true, then I could go through with the evaluation. Okay, so this is just me evaluating. So I would take, I'm going to back up here. Let's practice with the radicals before we move on to that, just to make sure we can do it, because as we know, a lot of multiple choice answers have what I call back of the book answers, but that just typically means they've been simplified until they can't be simplified any further. So I'm going to go ahead and do that here and practice saying 2 root 2 cosine of 5 pi over 4 plus I, and then I'm going to have 2 root 2 sine of 5 pi over 4. And that's probably the way you're going to see it more times than not, is in that simplified version. So I just want to make sure you can practice getting from here to here. That's a skill you're supposed to come to me knowing. So hopefully you do, and that's good. All right, so now let's just prove that all of this right here is in fact 2, negative 2, negative 2. And so we do that by looking at the fact that this 5 pi over 4 is a unit circle value. And so I can evaluate this and get a numerical value. So I'm going to say 2 root 2 over 1 times, and the cosine of negative 5 pi over 4 is negative root 2 over 2. So if I simplify this right here, then I can get my value. So 2 is going to cancel with my 2 right here and here. See, right here and here. And then square root of 2 times square root of 2 is square root of 4, which is 2. And the negative in front makes that equal negative 2. All right, then I do the same thing over here. I'm not going to forget about my I, but I'm just going to work on the inside right now. So that's going to be I times, and then I'm going to have 2 root 2 over 1 times, and the sign of 5 pi over 4 is negative root 2 over 2. So I can clean that up inside, and I can simplify this 2 with this 2. Square root of 2 times square root of 2 is square root of 4, and it's negative, so this is also negative 2. So what was the rectangular point? Was negative 2, negative 2, right? So this is just a way to check your work, right? I can just go back and evaluate it. So this is the polar system. This is the rectangular system. And again, I only did this because I just wanted you to see that this crazy thing we just calculated here does in fact produce that negative 2, negative 2 at the top. Okay, so last one, guys. A complex number is represented by a point on the complex plane using polar coordinates. The complex number can be written like this. Express the complex number using rectangular coordinates. All right, so then what do we need for them to be rectangular XY coordinates? We need to know what X is, and we need to know what Y is. So what are our conversion facts for X and Y? X equals R cosine theta, and for Y, Y equals R sine theta. So those are the conversions that I'm using. So I'm going to start by finding X first. So remember, we're using R cosine theta. So in the case of my particular problem, what is my R going to be? And we can see the R from this form is 4. So we're going to say 4. And then cosine. And then what's my angle? 7 pi over 6. So that's my setup there. And so X can equal 4 times, and the cosine of 7 pi over 6 is negative root 3 over 2. And so that's going to simplify, and leave me with 2 going into 4 2 times. So x is going to equal negative 2 root 3. Does that make sense? Well, where is angle 7 pi over 4? 7 pi over 4 is going to be down here. I'm sorry, 7 pi over 6. So from here to here is 7 pi over 6. And then I'm going to be going 1, 2, 3, 4 down. So I'm talking about that point. So then that does make sense for my x coordinate because I would be going in the negative direction. Then to find the y, I would say y equals r sine theta. So then y is going to equal 4 sine of 7 pi over 6. And we know that y equals 4 times, and the sine of 7 pi over 6 is negative 1/2, which I'm running out of room here, so I'm going to do my notation and do my negative 2 right here. Usually I don't like to do that, but if I try to write down here, it's going to go off the page for us. And so now I have my x and I have my y. So I know that the rectangular coordinate, which is what it asked me to find right here, is going to be negative 2 root 3, negative 2. And that's the rectangular coordinate. And that's how you do it. Okay, so I need you to practice making sure you know what models to use to convert back and forth. I need you to be able to graph or answer questions about multiple representation of a coordinate point. So those are the big takeaways for today. The fact that we can coordinate and write multiple forms of a single point. Making sure that we realize that it's not a negative r, it's just r in the negative direction. And then being able to look at the complex form in a rectangular system and also in the polar system. All right, guys, that takes care of it. You should have some check for understanding problems to do. It's really important to get this down because our next lesson is on polar equations, and you really need to have a fairly good knowledge of polar coordinates, or it can be a little more complicated than I want it to be for you. All right, thanks so much, guys. See you next time. Bye.